You ever stop and think about what makes butter so perfect for spreading on toast? Or what gives a really good chocolate bar that amazing snap before it just melts away in your mouth? Well, it's not some secret ingredient. It's actually secret architecture. It all comes down to texture. And we're going to dive into the tiny, invisible world that shapes the food we absolutely love.
I mean, we've all been there, right? You bite into a piece of chocolate and it's just perfect, silky smooth. Then you try another brand and it feels kind of sandy and just wrong. The reason for that huge difference is exactly what we're getting into today. And believe me, the answer is way smaller and way more fascinating than you probably think.
Okay, so here's the catch. The main thing that gives us all those incredible textures, we're talking about saturated fat, is the very same thing that we're all told to cut back on for our health. This creates a huge headache for the food industry. How do you give people that creamy, satisfying food they crave, but without all the saturated fat? And this isn't just about making food taste good, you know? It's a massive public health issue. You look at a map like this and you can see that things like obesity and heart disease are a global concern. So there's this huge push for scientists to figure out how to make our food healthier without making it taste, well, terrible. So where does the solution to this giant problem come from? Well, it's not some new wonder ingredient from a faraway land. Nope. The answer is hidden at a level you can't even see with your naked eye. We're talking about the world of microscopic fat crystals. All right, let's zoom way in. To really get how texture is made, we need to meet the little guys doing all the work. The actual building blocks that create the entire structure of solid fats. And here they are. They're called triglycerides. Now, the most important thing to know about them is their shape. They look kind of like a tuning fork. And that shape is absolutely crucial because it determines exactly how they can stack and pack together to form solid crystals. They're like little puzzle pieces. But here's where it gets really interesting. These triglyceride tuning forks don't just stack together one way. Think about it like having a pile of Lego bricks. You can use the very same bricks to build all sorts of different things, right? It's the same with fat. They can pack together in different arrangements, and in science, that's called polymorphism. So these are the three main ways they can pack. We call them alpha, beta prime, and beta. At first glance, they might not look that different, but trust me, these tiny little shifts in how the molecules line up have huge consequences for the texture that we actually feel when we eat. Let's think of them as having personalities. Alpha is the quick, unstable one. It's the first to show up to the party, but it never sticks around. Beta prime. Now, this one is the hero for smooth food. It forms these tiny, delicate crystals that give us the creamy texture we love in margarine or frosting. And then there's beta. Beta is kind of the villain. It's super stable, but it forms big, chunky crystals. You know that chalky, gritty stuff you sometimes see on old chocolate? That's called bloom, and it's basically the beta form taking over. So how do we get from these individual tiny crystals to, say, a solid stick of margarine? Well, it's all about how these little guys link up together to form a giant interconnected web. It all happens in three main steps. First up is nucleation. Think of it like the very first snowflake forming in a cloud. Just a few molecules huddle together and create a stable little seed. Then comes crystal growth, where more and more molecules see that seed and start attaching themselves to it. And finally, you get network formation, where all these growing crystals start to tangle up and interlock. And this is what the final result looks like under a microscope. You can see just how complex and branched this network is. Now, this whole structure basically acts like a tiny sponge, and it traps liquid oil in all those little gaps. That's what makes something like margarine feel solid, even though a huge chunk of it is actually liquid oil. Okay, so if this is just a natural process, how do we get any say in it? Well, this is where food science gets really, really cool. Scientists have figured out a whole toolkit to basically tame these crystals and build the exact textures they're looking for. They've got two main levers they can pull. First, they can tweak the ingredients, adding things like special waxes or emulsifiers that can guide how the crystals form. The second lever is changing the process itself, controlling things like how fast you cool the mixture or how much you stir it. Check this out. This is a perfect example of changing the ingredients. On the left, if you add some rice bran wax to an oil, you get this beautiful network of fine needle-like crystals. But on the right, if you use candelilla wax instead, you get these bigger, more clumped together structures. Same oil, two different waxes, and you get two completely different textures. And this is what happens when you play with the process. If you cool the fat down really slowly, you give the molecules a ton of time to find each other and grow into big crystals. So you get fewer but larger crystals, which can feel gritty. But if you crash cool it really fast, you force a ton of tiny crystals to form all at once, and that gives you a much, much smoother product in the end. So let's bring it all back to where we started this whole thing. Why does being a master of this microscopic world even matter? Well, because it gives us a way to solve that big saturated fat dilemma. And here it is, the big payoff. The research shows that by getting this crystallization process just right, by literally designing the fat network from the molecule up, you can create that same firm, spreadable texture while cutting the saturated fat by an incredible 50%. And you don't have to take my word for it. This quote from the research itself says it perfectly. By controlling both the ingredients and the process, they could design a final texture that let them slash saturated fat in half without losing that network strength. They're basically building a stronger house with half the bricks. It's a game changer. So what this really means is that we're moving beyond just mixing ingredients together. We're becoming food architects at the molecular level. And if we can design the perfect crystal network for a healthier butter substitute, just imagine what other foods and textures could be engineered next. The future of food is quite literally being built one tiny crystal at a time.